This is week 3 of this course. Welcome to this session, and we are going to look at forced oscillator this week. All the while in the first week we saw about the simple harmonic oscillator and its properties. In the second week we looked at the damped oscillator and various properties. Just to quickly recap what we had been doing in the last week, we wrote down the equation of motion for a damped oscillator, which is this, and to remind you again, this gamma here is the dissipation coefficient, and we also obtained the solution for this equation of motion, and depending on the value of the quantity here inside the square root, you either get damped oscillation or you simply get no oscillation at all. So, in other words, I have tried to summarize what we saw. So, there was the first case which we simply called as a case of heavy damping. So, that happens when this condition is satisfied, this one here, and in this case the displacement as a function of time is shown here. So, you give it a push, it goes to certain distance and comes back towards the equilibrium position. There is a second case when which is called the case of critical damping, and it is characterized by this relation between the parameters. So, in this case again there are no oscillations. On the other hand, if you had chosen your parameters which satisfy this relation, in that case you get damped oscillations, and it is sketched here. So, you see that you do have oscillations whose amplitudes successively are reducing. So, what you have is damping, energy is being lost from the system. So, these are the three possible cases we saw in the case of damped oscillator. It only means that left to itself the system would simply dissipate the energy to the surroundings, but you can maintain the energy by giving it continuous supply of energy, which is what you do for instance in a clock with a pendulum. As such, without an external source of energy either from a battery or in a more mechanical clock, one actually turns the key and so on, which stores the energy and supplies it. So, if you do not do any of that, the clock would not work beyond a few seconds, but when you supply energy you can make it work, and it does give periodic oscillations, which is what the remit of this module, which is to look at the forced oscillator. So, essentially we need to model the idea that we are continuously giving it energy. And here if you look at the equation of motion that I have written down, it looks very similar to the damped oscillator except for this part on the right hand side. So, F0 is the amplitude of forcing. So, this term on the right hand side tells you that you are supplying energy as a function of time. So, in this case the model that we have written down says that F0 is the amplitude of oscillation, and there is a cosine or cos omega t attached to it. So, the external force that you are supplying oscillates in a sinusoidal manner. The difference between the damped oscillator and the forced oscillator is what is given here on the right hand side. So, this is the case of equation of motion for a damped oscillator, and this one is the equation of motion for a forced and damped oscillator, and for short we will just call it the forced oscillator. The first question that we will be asking is, why did we choose this particular form of forcing, this particular form of external forcing? It could have been anything else. So, the reason is I could have chosen it as F0 cos omega t or F0 sin omega t, or even much more complicated function. So, in general it could have been some function of time, not necessarily cos or sine. But the good thing about this is that if I choose any arbitrary function, I can always decompose it in terms of sine and cosine functions through what is called a Fourier transformation. And if I do that, in general, the central and the simpler problem that I need to solve is what is written here, essentially this. So, if I can solve this, I have essentially solved a problem for a general forcing, which is f of t. So, it is enough if I know how to solve a cosine or a sine kind of forcing. So, that is the first aspect that we should keep in mind. It is not very restrictive. In fact, we are trying to solve a fairly general problem. Now, we are interested in solving this equation. So, let us see how we go about solving this equation, which is essentially what we are going to do in this module. So, I have both the versions of oscillator. So, this is a damped oscillator on the right hand side, and on the left hand side I have the damped and forced oscillator. This damped and forced oscillator is what would be called non-homogeneous second order ODE. So, ODE stands for ordinary differential equation. In contrast to an equation like the case of damped oscillator here, this is a class of what is called homogeneous second order ordinary differential equation. So, these are two distinct classes of still second order ordinary differential equations. And now, to solve the case of forced oscillator, what we know from this class of differential equation is that the general solution for this class could be written like this: x of t, let me write it as x c of t plus x p of t. So, here x c of t is let me give numbers to it. So, let me say that this is equation 1 and this is equation 2. X c of t is simply the solution of equation 2 and x p of t is any solution of equation 1. But we know the solution of equation 2 already, because we solved it and we had written down and analyzed it in the previous modules. So, whatever we had already solved for the damped oscillator would be part of the general solution for the forced oscillator. So, this is called the complementary solution, which is why I had put this C here, and this x of p is called the particular solution. So, the general solution of a non-homogeneous second order ordinary differential equation consists of two parts. One is the solution of equation 1 with the right hand side set to 0, which is simply the solution of the corresponding homogeneous part, plus you somehow find out any one solution for the full forced oscillator. You add these two components together and that shall be your general solution. In the context of the kind of oscillator problem that we are looking at it, we can look at this solution in a little more physical sense. X c here is simply the complementary solution, and this complementary solution is just the solution of the damped oscillator. And what we know from the damped oscillator solution is that, like we just did a recap of those, in all those cases, whatever be the various parameters that you might choose, as time tends to infinity, there is no oscillation in the system. So, if you even for this case, if you if you wait for long enough time, the oscillations would have died down. So, in all the cases that we meet, the oscillation does die down, and clearly the reason is because xc of t has this e power minus p t term, and this kills oscillation as time tends to infinity. So, if you wait for long enough time, you will not see any oscillation. So, this kind of a behavior is what would be called transient. The reason it is transient is because you do get oscillation, but it stays only for a short time for a particular choice of parameters. Now, what about this second part x p of t? So, in this case again we need to see what is it that is physically happening in the system. I have an oscillatory system and it is getting damped because of dissipative forces, but I am trying to give it some energy externally, and the process of giving it an external forcing is modulated by a cosine function. So, there is a frequency omega with which I am driving it. It is like, imagine a physical situation like you go to a garden and there is a swing, and every now and then you give the swing a push to keep it oscillating. Now, the frequency with which you are doing is the so called driving frequency, and here this omega is the driving frequency. Now, ultimately if you are doing this, just imagine what would happen to the system. The system has its own dynamics, in the sense that if you do not disturb the system, it will oscillate at its own frequency. You can call it the natural frequency of the system, but now you are trying to interfere and forcing a different kind of frequency on it. So, ultimately there would be sort of some negotiation between these two opposing forces, and finally after some amount of time the system would precisely oscillate at the frequency at which you are driving it. So, what you can expect from the second part of the solution, which is called the particular solution, is that maybe there would be a sort of steady state established between these two opposing tendencies, or these two tendencies which are not quite in consonant with one another. So, you could expect steady state as a possible solution. So, just to keep this in mind, let me repeat that the complementary solution is a transient which dies away after some time, simply because oscillation or a small movement away from the equilibrium dies off very fast, and after that there is no contribution from this term which is represented by x c of t. On the other hand, the particular solution is a steady state solution, because it is equivalent to saying that the system finally responds to your driving and it also begins to oscillate with the same frequency as the one with which you are driving it. And to complete the story on the right hand side, so the solution of the damped oscillator, I will take it as x c of t, and we have seen all these properties earlier on. Now, with this understanding, we are going to concentrate on the steady state solution, namely what happens to a forced oscillator as time tends to infinity. So, we are not so much interested in the transients, which are anyway going to die down after a short amount of time. We are interested in what happens in the long time limit. So, we will be interested in working out this solution x p of t for the case of forced oscillator. Okay, let us now solve this equation of motion, and to solve this equation of motion I am going to do it a little more generally. Let me write the equation of motion here. In the way I have written down this equation, the right hand side is a complex number, and I shall assume that x double dot, x dot and x are also complex quantities. I am going to assume an ansatz for the solution x of t, and as we just now discussed, if I wait for certain amount of time until the transients die down and so on and so forth, after that you will see that the system also will display oscillation with angular frequency omega. In which case it is perfectly fine for me to assume that the displacement as a function of time is some a amplitude. Again remember that it will be complex because x itself is a complex number, a into e power I omega t. Once I know this, I am going to compute x dot of t, which will be a I omega e power I omega t, and x double dot of t will be I square will be minus 1 a omega square e power I omega t. Now, I need to plug in these three quantities back in this equation and find out for what value of a all this is satisfied. So, if I do that, you can cancel out e power I omega t on both sides. I should be able to get the following equation. So, a little bit of manipulation would give you this form of a. Now, I am going to manipulate it a little bit. I will multiply and divide by minus I. So, you would have now understood as to why I did this, because I wanted to get this form in here. And if you remember, the quantity that we have here in the denominator looks like the definition of impedance that we saw in the previous module, and it is indeed the impedance that we defined in the last module. So, I can write this as minus I f 0 into omega z, where this quantity z is. So, should remember that z being the impedance complex quantity as we see here, and now we have the amplitude, which is also a complex number in a form that is somewhat useful for us to now write the solutions. Now, with this I am nearly done, can write the solutions. So, x of t for example would simply be a into e power I omega t, which means that it is. So, I have obtained a solution which is displacement as a function of time. And to make this a little more meaningful and explicit, I want to write z in a slightly different form. Impedance, which is z, remember that it is a complex number, I can write it as mod of z times e power I phi. We will define what phi is shortly, but if this is the complex number which is the impedance, it is easy to figure out what phi is. We have done these manipulations again in the previous module. Now, let me insert this in my expression for x of t, and this will be minus I f 0 omega mod z e power I into omega t minus phi. So, now I have the solution for displacement as a function of time. So, I have the solution for displacement written here, and modulus of z, which is the magnitude of impedance, is also written here, and tan phi, from which we can actually extract phi, would be given by m omega minus s by omega by gamma. Okay. So, we have everything in place to explicitly say something about the displacement, okay, which is given by this formula. Now, let us look at the solution a little more carefully. So, the first thing is that, as we expected, it turns out that the displacement as a function of time is an oscillatory function, and the frequency of oscillation is omega, which is actually the frequency with which you are driving the system. Remember that you have this omega here. So, you drive the system externally with frequency omega, and finally, the system also responds in the same frequency. Displacement has the same oscillatory frequency omega. And just to make some comparisons, let me say that my external forcing is f0 into e power I omega t. So, frequencies match, but what about the phases? So, you would see that the displacement and the external forcing, they are not quite in phase with one another. So, the first thing that you notice is that with respect to the external forcing, displacement x of t has this additional phase which is phi attached to it, and the magnitude would depend on the value of these parameters m, s and gamma. So, there will always be a phase difference of phi between the external forcing and the displacement in a forced oscillator. So, the first lesson is that the external forcing and displacement, they have the same angular frequency. Second lesson is that there would be a phase difference of phi between forcing and displacement, and that you can figure out from these two equations, one for x of t and the external forcing which is f0 e power I omega t. So, this and this. And another point to note is that suppose even by chance if phi were equal to 0, still there would be a phase difference because of this minus I term which is here. That would ensure that still there is a phase difference of pi by 2 at least between the external forcing and the displacement. So, even if phi is 0, you can always choose parameters such that phi is 0, but even in such a case there would be a phase difference of pi by 2 between the displacement and the external forcing. In fact, more precisely, displacement would lag by a phase of pi by 2 with respect to external forcing. The maximum amplitude of displacement is f0 by omega into mod z, which is given here. Okay. So, with these four sort of basic lessons that we have learned from the analysis that we did, now we can go and actually write down an explicit form of solution, which is which more or less conveys everything that we have tried to infer here. Let me say that now I am trying to solve this problem m x double dot plus gamma x dot plus s x is equal to f0 sin omega t. So, I want to solve this problem specifically for the kind of drive that is written here, which is f0 sin omega t. If you go back and look at the problem that we actually tried to solve for, the forcing there was f0 e power I omega t, which means that it is actually f0 cos omega t plus I f0 sin omega t. So, in some sense we have already solved for both cosine and sinusoidal driving. All we need to do is to isolate the solution only for f0 sin omega t kind of driving. So, all I need to do is to copy the result that I have obtained for the displacement. Let me write that down to begin with. So, x of t was, and this is the solution that we had. So, again let me emphasize that x is the complex quantity, which means that this could have been written as, let me now multiply minus I inside, in which case I will get f0 by omega mod z and minus I cos omega t minus phi minus I when multiplied would give me plus 1, and that would simply boil down to this. All I need to now do is to recognize that this f0 sin omega t, which is the particular choice that I made for the external driving, and I need to correlate with the kind of external driving that I have put in here. So, this will be f0 cos omega t plus I sin omega t. So, the correct solution that I expect should all be imaginary part of the solution, because the forcing here appears in the with the I here, which means that for this form of external driving, now the solution can be written as x of t is equal to f0 by omega mod z into of course, there is a minus sign cos omega t minus phi. So, now it is very easy for me to generalize the result. If forcing is of the form f0 sin omega t, then my solution is minus f0 by omega mod z cos omega t minus phi. On the other hand, if forcing is f0 cos omega t, in that case the solution x of t would be the real part of this one, which would simply be f0 by omega mod z into sin omega t minus phi. So, as I said, we have solved two different problems when we treated this as a complex quantity. Having obtained the displacement as a function of time, now it is easy to also find the velocity as a function of time. The velocity as a function of time, which I am indicating by v of t, would simply be the first derivative of this function, that is I f0 by omega mod z will give me I omega into e power I omega t minus phi, and omega would cancel, I square is minus 1, combined with the minus sign there, I will simply have f0 by mod z into e power I omega t minus phi. So, this is velocity as a function of time. So, once again we can ask, what if my forcing is f0 sin omega t and f0 cos omega t. So, if forcing is f0 sin omega t, I just need to take the imaginary part of this quantity, and in that case v of t would be equal to f0 by mod z into sin omega t minus phi. And similarly, if external forcing is f0 cos omega t, in that case v of t will be the real part of this result, that will be f0 by mod z into cos omega t minus phi. With this, we have obtained the solution for velocity. So, now if I analyze these expressions for velocity a little more closely, you will see that between the forcing that I have and the expression for the velocity that I have obtained, there is always a phase difference of phi. So, whether you take your forcing to be f 0 sin omega t or f 0 cos omega t, in either case there is going to be a phase difference of phi. So, the velocity and the external forcing would differ in phase by phi, but if you choose parameters such that phi is equal to 0, in that case the forcing and velocity would be in phase with one another. Again, it does not depend on what form of forcing that you choose. And just to remind you once again, phi is given by m omega minus s by omega divided by gamma. So, if you want to find phi, we just need to take tan inverse of this quantity. To summarize, let us just collect the results together. We solved the equation in complex form. So, we have results for both kinds of forcing, f 0 sin omega t and f 0 cos omega t. So, let me for example assume that forcing is f 0 cos omega t. If this is the external forcing, now my equation of motion would be m x double dot plus gamma x dot plus s So, this is a scalar equation, all the quantities are scalar. In such a case, what we saw was displacement as a function of time would be f 0, which is the magnitude of external forcing, divided by omega into mod z into sin omega t minus phi. And we also saw that velocity will be v of t, which will be equal to f 0 by mod z into cos omega t minus phi. And clearly you notice that between the forcing and displacement, one is a cos omega t and other is sin omega t. So, even if phi were 0, there is going to be a pi by 2 phase difference, but between forcing and velocity, if phi is 0, both would be in phase, otherwise there would be a phase difference of phi between velocity and forcing. And with this summary, we will go and see some more properties of the forced oscillator in the subsequent modules.